So I really like this lecture, or at least I like the topics in the lecture. Hopefully you find it interesting as well. Talking a little bit about game performance, specifically when it comes to memory, and why you may want to consider how your memory is actually being stored in the game, because it turned out that everything you've been taught in computer science doesn't matter if your code is not cache friendly. So we'll see why that is. So there's many factors, of course, that determine the overall performance of our game. With the ECS architecture that we've been talking about so far, we can very easily profile our systems independently to determine which are bottlenecking the program's speed. So one of the cool things about not having a monolithic single function game and splitting it up nicely and modularly into these systems is that you've seen so far with the pause functionality, for example, you can easily turn on or off specific functions in the game. So, for example, if you want to profile the functions of your code to see which, or the functions in your game, to see which are slowing it down, which are running okay, you can even like turn off the rendering and run the game engine as fast as possible. There's lots of cool stuff that you can do with the architecture. Now that's not saying that you need ECS in order to do that. It's just saying with the architecture we've introduced, it's very easy to do that. And so typical bottlenecks in your program are physics calculations, meaning things interacting with each other. We've got loops like for all the tiles, maybe they have to collide with other tiles, etc. AI systems in, not in our game because our AI is very, very simple, but in bigger games, the AI could be the bottleneck. Maybe the rendering is the bottleneck. Modern AAA games have like 10 different pipelines going to the GPU for all these different layers of special effects and stuff. Ray casting is in pretty much every single game for some reason, so lots of lighting effects, lots of bullet line of sight calculations, stuff like that. So what you do is you run some sort of profiler on your code. You're not meant to be able to read this, but this profiler will hopefully be able to tell you, okay, here's the running time of the different components of your system. And by components, I don't mean ECS components, but the different parts of your system. So, okay, here the drawing function is taking this amount of time, the physics function is taking this amount of time, and you can visually look at it and see, oh, okay, that's taking more time than I expected, what's wrong? Or that's performing well enough. And in one of the future lectures, I can't remember if it's the next one or the one after that, we'll actually be writing our own profiler. And it's remarkably simple and easy to use. But if you do want to watch some more about this, if you're actually interested in learning, these are some of the videos of the many hundreds, if not thousands of videos on the topics that I've seen over the course of the past few years. So the first one is what our profiler will be based on. So I watched that video and was inspired to take that code and clean it up a little bit and adapt it for our system. And there's many, many different videos out there. But there's also non-obvious performance hits. So it's easy to think that because we are good computer science students and we've all taken our algorithms class or our data structures class, that the only things that affect performance are the algorithms and the math, right? So, okay, the only thing that matters is getting from O of n to O log of n. And of course, that's somewhat true, right? Changing n squared to log n, if you have big n's, is going to save you a lot of time. So that's a necessary step, but it's not a sufficient step. It's not the only thing that we need to think of. And so in practice, the implementation of those algorithms can impact performance even more than the algorithms themselves. And why is that? Well, we'll see. So some important optimizations that we want to do in our systems, of course, use the most efficient algorithms. This is where computer science helps, but also kind of where computer science stops, right? You do your theoretical improvements, you write the answer on the exam, you get your marks, but you've never actually implemented it and saw how fast it was in comparison to other algorithms. All you've done is done a big O notation analysis of that algorithm, right? The results may surprise you. So another thing you can do is minimize the size of your data structures, right? Sometimes, if you're passing around like billions of 64-bit integers to store an integer that will never be bigger than 10, why not use a char, right? Why not pass around 8 times less data? Maybe that will help speed things up. Maybe it won't help speed things up. We'll see later that if you minimize the size of your data structures, you might get better cache performance, which would be excellent, which would really impact things. But in general, do some analysis on the size of your data structures and see if they couldn't be smaller. Now, in some really weird cases, like, the compiler or the compiler is generating code that's passing around 4 bytes at a time anyway, so if you have 2 bytes, it doesn't really matter. It's going to convert it to 4 bytes and then pass it as 4 bytes, but minimizing the data structure size is never bad. It's only bad in the case that, let's say, for example, in my game, my speed will never get higher than a 2-byte integer, so let's say 16,000, right? Therefore, let's use a short instead of a normal int. But then later on, you add some new feature to the game, and now there's a rocket that can go faster than that, right? And so it wrapped back around to the negative, so you got all these bugs in your code. So when you're doing this sort of minimization, don't go overboard with it, right? You've got to be careful about what you do. Code reuse and modularity is important as well. So we've seen, for example, one of the ways that we reuse code is by writing functions. So for example, if there's some functionality that you should have in your program that you're going to use multiple times over and over and over again, you probably shouldn't write those few lines of code every single time you want to do that thing. So one of the examples in our system was the creation of an entity, right? So you can think, okay, there's lots of different places that we want to create entities, but creating entities involves things like a little bit of bookkeeping. Where am I going to store it? How am I going to maintain its lifetime in memory? How am I going to delete that thing? And so we wouldn't want to have to do that every single time we want to create an entity. So we made this entity manager. And now there's this function, which is add entity. And what that does for us is if we go through and we figure out some new technique for optimizing the adding of an entity, if we make that change in that one function that we have to call, then now wherever we create an entity in our program, that is now optimized, right? Versus if we hadn't done that, if we're just creating entities willy-nilly all over the place, we would have had to go back and optimize the possibly hundreds of different places in our code where we were creating entities. And so this goes for any time we're doing anything like that, right? We have the vec2 normalize function. Well, instead of normalizing the vector in the code every single time doing the math, put it in a function, right? That modularity is more than just ease of programming. It's also good for optimization as well. Another thing is to minimize dynamic heap allocations. Later on, we're going to be talking about something called a memory pool that can help us with this. But if you're very familiar with C++ and you're watching, or if you're part of the class or you're watching the lectures, you've probably been cringing at the fact that we're using shared pointers for everything. Because every time we create a new shared pointer, this is a dynamic memory allocation, which is very slow. And we'll talk about that in a little bit. And also, there's the idea of writing cache-friendly code. And so if you're looking up memory in RAM and it's not in the cache, this is a surprisingly slow operation. And so data-oriented design and programming can come into play when you're looking at the memory layout for things in your program. Okay, so the first one is minimizing the data structure size. A good thing is that C++ gives us fine control over the data structures that we want to use for our games. Now, fine control is something that's often a benefit and often a detriment. If you use Python, I just want to do a quick calculation and not worry about whether the thing is an int or a long or an unsigned long. I just want to divide two numbers, right? But it's a good thing if you're really trying to optimize things. So deciding on a size type for your data depends entirely on the context for your program. And minimizing data structure size can help your game in several ways. So reducing size, obviously, less memory used. That's great, right? You use less RAM. You know, we've all got the Chrome memes where it's like you open up, you know, you have a few tabs open and Chrome is using like 30 gigs of RAM. You'd want that to be less if possible. Also, not as obvious is that reduced size of your data means less time spent copying your data. You're always passing parameters around, right? And so if those parameters are a bit smaller, then that's never a bad thing. Also, we talked about this before. If the size of your data is less than 8 bytes, just pass it by value. You don't need to pass it by reference because those dereferencing operations on every single time you pass something can actually add up to a surprisingly large performance hit. Okay, so here's a data size example. Let's say our game world size is 64 by 64. And we know that this is going to be the largest size of any map that our game will ever hold. Then we don't need a full int to store the player's location, right? So let's say we've got an unsigned char for the x and the y. That's 1 byte each, right? So we've gone from, okay, an integer is going to be 4 bytes. On a 64-bit system, by default, it might be 8 bytes, right? So if we went from 8 bytes to 1 byte, we have now divided this, or we've reduced the size that's required to store this particular piece of data from 8 to 1. But the point I've been trying to make is that later on, maybe there's a new expansion, and there's a bigger map, right? And so if you're using an unsigned char, now your biggest x value is 255. So if you've got a map that's bigger than 255, you've got problems. But if you've written your code in a modular way, there should be one place in your code, like for example, you've got a grid location type def or something like that, and you can type def that from the uchar, which it was, into an integer now because you need that bigger space. So code modularity comes into play here as well. And so basically, what people do in practice is let's choose the bigger data type to start out with. And then once everything works and we're sure all the features are locked down, then we can start playing around with the optimization. So don't start this by using an unsigned char, right? Make sure your program works with a larger data type, and then later on, when you start profiling and you start performance, so there's writing the program, getting all the features implemented. Then there's the testing of all those features to see if they're working correctly. And then there's the optimization of those features. I'm sure you've heard, premature optimization, that term before. It means you're optimizing things before you know that they actually work. And optimization sometimes can take some time, and you'd rather have the features, like it's no good to have an unfinished game run really fast, right? So don't spend all your time on optimization right away. Make sure that all your features work first. Code reuse and modularity. So we've talked about this before. Anytime you have to do the same thing twice, in my opinion, have a function for it. It's a pretty decent rule. If you're like hyper-optimizing some small piece of physics code, maybe you would want to do the manual calculations yourself. If you run the profiler and see that that's the case and it's faster, then okay. If you're generating the assembly code and manually inspecting it and seeing that the overhead of the stack call for the function call to do two things is not really that optimal, your compiler is usually pretty smart, right? You have a function to make your code look better, and then you can inline that function if you want to get all the performance benefits of not having the function call, right? So basically, wherever you're doing a couple of things in a row that are the same thing, to put it in a function. And then, anytime you want to optimize that process, you do it in the function, and it's in a single place, right? So we just talked about this. We use the entity manager all the time without knowing how it has to work. And if you were actually at some company somewhere, and you're doing like the gameplay functionality, you're doing the physics calculation, you're probably not the person who wrote the entity manager, right? So you don't need to know how it works necessarily, but you do know that, hey, that functionality is there in that one spot that I need, and then the entity manager people can talk to the back-end memory pool people and make sure that that's an optimized process. Any optimizations made to that entity manager are completely invisible and ideally don't require any top-level changes, meaning like in the gameplay code or something like this. And I'll show an example of this a bit later. Next, I talked about dynamic memory allocations. So dynamic heap allocations are expensive. So whenever we use a shared pointer, whenever we say object star O equals new object, those call malloc, which is the memory allocation function in C or C++, and that is completely dependent on the operating system. And what happens is it goes out and tries to find a contiguous block of memory for a given size, and then given the complexities of memory layout, it's much, much, much slower than allocating that memory on the stack. And I'm not sure, I think I may have showed this before, but this is what happens for malloc, right? This is the logic flow of that, I think, on Linux. Could be different, could be way worse in Windows, I'm not sure. And then even when you want to free something, all this stuff is going on, right? When you want to reallocate some memory, all this stuff is going on. So all of this happens, right, when you create a new vector, for example. Then down here, whenever your vector gets full and it needs to resize itself, realloc is happening. And then when that vector goes out of scope, this is happening, right? So vectors are fine, but if they resize often, then that's a whole bunch of memory allocations that you probably don't want happening. And we'd like something like this happening, right, where we could have really performant games where we're creating, tens of thousands, if not hundreds of thousands of things, and they're just like popping in and out of existence. If each of these was a dynamic memory allocation, this game would run a lot slower. Now, it is in your game engine, but this is a modified version of the engine that I created. Okay, so how could we possibly go about reducing dynamic memory allocations? That's a hard problem. You're like, well, I need some amount of memory. Maybe it's more than what's available on the stack, right? So I can't use stack allocations for everything. One, because there's not enough memory available on the stack. And two, because if I allocate it on the stack, as soon as that goes out of scope, I no longer have access to that variable, right? So there's reasons why we don't just stack allocate everything. So heap memory is too slow to allocate often, and stack memory is too limited. So it's like, well, you're damned if you do and you're damned if you don't, right? But what we could do is allocate a large chunk of heap memory at the start of the program and then use only that space that we've already pre-allocated. So the program starts up, we're saying, okay, how much memory do I want to use? Well, let's say, okay, I'm going to take 2 gigs of memory. I'm going to set that aside, and now wherever I'm going to want to create entities, it's going to go into that section of memory. And what you can do, this is going to eliminate the dynamic allocations of memory during runtime, if you do it correctly, because you can say, okay, now I've got my own custom data structure. So this does come at a programming cost. Like implementing your own memory pool is not a trivial thing, right? Now, what you've done is you've said, okay, I've eliminated the dynamic memory allocations because I've got my heap memory allocated. It's there, right? But this comes at the extra complexity of managing that memory pool, because you can no longer just say new, right, and have the operating system give you the memory. You've got to be able to say, okay, where in this memory pool am I actually going to store this thing? Now, it turns out that if you construct your memory pool in a decent way, and luckily for us, ECS allows us to do this in very easy ways that let us manage that memory both efficiently, effectively, and kind of easy to program. What we can do is create a big vector for all of our entities, right? And that vector we know will never resize, and we can just change the properties of things in the vector. So it does come at the added complexity of having to create this memory pool for yourself. But the cool thing is that because that memory pool is doing a very specific thing, like only storing entities, for example, the complexity or the efficiency of that structure, because it's very specialized, is much better than a generic call to your operating system to give you memory. But we'll get back to memory pooling at the end once we've talked a bit about cache memory and why that's very important. So cache coherency. Cache coherency is the idea that your code is being friendly with the cache. And what do we mean by that? Well, writing cache-friendly code is one of the most important speed optimizations in practice that you will ever come across in all of your programming. So the idea of what the cache is doing is that when you fetch data from RAM, surrounding values are also fetched. So for example, now these values are not exact, but it's maybe a bit older than the current generation of hardware. So the numbers may be bigger now, but the idea is still the same. If I look up this integer in my array, the computer is not just getting that one 4-byte integer. It's also getting, well, it's getting maybe 64 bytes worth of integers, right? That is what it has actually fetched. And then if you get the next integer, it's already in cache, and so it just looks in the cache rather than going back to the RAM. So cache memory is much faster, it's physically closer, but is much smaller than normal RAM, right? So there's always trade-offs. So heap memory, very large, but very slow. Stack memory, very fast, but very small. In a similar way, they don't operate similarly, but in a similar way, cache memory is much faster. It's much more expensive. That's why your whole computer isn't just cache memory. And it's also physically closer, but very, very, very small. You can't just fit your whole game in cache. So if you organize frequently used data contiguously, meaning literally right next to each other in the address space of memory, then when you go to get that memory, you'll be getting big chunks of it, and so you'll get more cache hits. So whenever something is in the cache, it's called a cache hit, and when something is not in the cache, that's called a cache miss. And cache misses can be surprisingly expensive. So what happens when you try and access data in your code? And this is true of heap memory as well as stack memory. But stack memory is usually, stack memory, if you have a bunch of variables on the stack, they're usually cached together anyway. So this is typically when you're talking about heap memory. But when you access any data from any part of memory in the code, the following sequence of events occurs. So first, the data is looked up in the L1 cache, then the L2 cache, then the L3 cache, and if it's not anywhere in any of those, well, if it's in L1, it stops. It found it. Then it looks in L2. If it finds it there, then it stops. It found it. Then it looks in L3. If it finds it there, it stops. It found it. Otherwise, it looks it up in DRAM. And I haven't found a great video yet to actually explain like the implementation of cache. Like, hey, how does it know that what I just wanted is in the cache or not? And so I was talking to someone last night about this who knows more about it than I do. And essentially, there's like a hash table. It's like a really efficient hardware implementation of a hash table. So the memory address that you look up in RAM is like the index to that thing in cache, right? And so it looks up, okay, Dave wants the thing at address 71. So look up if that value is hashed in L1 cache, and then there's 64 bytes ready to go in L1 that it pulls from there, if so. And if that's true, then it says don't look it up anywhere else. So it's something along the lines of a super efficient hardware implementation of a hash table. Here's what this looks like in sort of an abstract view, where you've got each core of your CPU, in modern architecture at least, has its own L1 and L2 cache. So each CPU, or each core of a CPU, has its own L1 and L2 cache. Like a decade or more ago, maybe only the L1 was on each CPU, and the L2 was off of the CPU. So it was like on the motherboard rather than on the CPU. But nowadays, each core has its own L1 and L2 cache. And then there's a shared L3 cache that all CPUs share. And then, of course, there's main memory, which is sitting like a whole 6 inches away, right? And when you're talking about these speeds, which we'll show in a second, some examples of these speeds, like the physical distance that electricity has to travel starts mattering, right? So just having the cache on the CPU is like the speed of light is really fast, but it's not instantaneous. and we're talking about billions of things happening per second, then the speed of light starts to be like not slow, but not instantaneous, right? And so if you look at like a modern processor, this is sort of what's happening, right? The memory and CPUs are laid out in a specific way such that the caches are physically more close to these CPUs. So you'd have a CPU core where the operations are being done, then you'd have like the registers which are inside the CPU, and then L1 and L2 cache which are on the same chip but not directly as close as the registers, and then you'd have some L3 cache that, and other things there. So if you look at an actual processor, if you look at like the die of the processor, this is true. So I can't remember exactly what processor this is, but even if you're looking at like a modern Mac Silicon, it kind of looks something similar to this. But they've got the GPU on there as well and all sorts of crazy stuff because it's like system on a chip. But most modern processors have some sort of layout like this where you have the actual CPU core, and then physically right next to it is the L1 cache. And then physically right next to that is the L2 cache. And it's a little bit bigger. You can see that it's physically bigger. And then you've got this shared L3 cache as well. So ideally, all of your lookups, past the first one are going to be in cache. That's impossible in practice, but that's what you would want to happen. So just some examples of numbers. I got this from this like Brown University, someone's lab. I was looking for sample numbers, and these are good enough. The numbers, the absolute values here, like 0.3 nanoseconds, that's not as important as the comparative values, right? So registers are like right there. They're super fast. You can never beat a register. It's part of the CPU. But L1 cache access is on the order of a nanosecond, right? Nanosecond, very, very fast. If we go down to L2 cache, 3 times as slow already for L2 cache, another 4 times as slow for L3 cache, and then, okay, maybe you have L4 cache, maybe you don't. But the main memory, like very fast memory, you're still on the order of 50 to 100 times slower than cache memory, right? Which is insane if you think about it. And then you've got like solid state drives, which is like 1,000 nanoseconds, and then, a hard disk drive where you basically don't want to be reading from a spinning disk anymore. Okay. But why is the cache so fast, and why don't we have more of it? Well, it has to do with like the physical limits of the universe and the properties of these like metals and things. But essentially, you've got 2 types of memory in your system. You've got ROM, read-only memory. You've got RAM, which is random access memory, which you can read and write to. And within RAM, you've got SRAM and you've got DRAM. So what is this? Well, DRAM is called dynamic random access memory. It's used in your main system memory, so you install a RAM chip, that is DRAM. Or if you have an Apple computer, you don't install anything and you can't take out anything, right? It's there. But your main system memory is usually DRAM. And the main difference between DRAM and SRAM is like how it uses electricity to actually store information. And so DRAM, the data is stored in capacitors. And I'm not about to get into electricity and stuff like that because I don't know a lot about it. But essentially, a capacitor is charged, and over time, it loses its charge. And so you actually have a physical memory controller for DRAM, which says, oh, it's been a while since this got a charge it up again. And so what happens is this uses more power, therefore it's a little bit slower, generates more heat, which needs to be dissipated. And so it's just slower than static RAM. It's still faster than disk, right? But these capacitor technologies are just not as good as SRAM. So the good thing, because there's always a trade-off, right? Nothing is always best. Lower cost per byte. You can have gigabytes of DRAM, but you're not going to get gigabytes of SRAM, at least not yet, right? If I watch this lecture 10 years from now, it might not be the case, but right now we certainly don't have that. So it's slower than SRAM, but it's less expensive. So SRAM, if you saw the D for dynamic, you maybe already guessed that S is static random access memory, typically used in cache memory and in other places on the bus where things need to go fast. It stores data in flip-flops, not the things you wear on your feet, but the computer-signed flip-flop, which do not need refreshing like capacitors in dynamic RAM. And so it's a higher cost per byte, it's a more expensive technology, but it's much faster. You just saw some examples, could be 50, 100 times faster. Or back in the day when dynamic RAM was even slower, it may have been even like hundreds of times faster. But it is used in conjunction with DRAM for a balance, because we could not have a modern computer which operated solely on static RAM, because, you know, if this ever existed, maybe it's in some like military technology where the whole thing is static RAM to be as fast as physically possible, but certainly not on any commercially available machines. So a cache miss, they're very expensive. Here's an example calculation that I put up here, I don't know, 5 or 6 years ago. It was fairly accurate then, but it's just an example to show you how bad this stuff can be. A cache miss is approximately 200 CPU cycles. A multiplication is approximately 3 CPU cycles. So you may think that when you're writing your program, right, that you've really got to hardcore optimize. Get that one subtraction out of there, right? Get that one multiplication out of there. Get that division out of there. Now, it's important, of course. It will possibly speed it up. It's always best to have the best algorithm, to have the most optimized piece of code. But you can do 65 multiplications in the same time that it takes you to look up a value in RAM if it's not cached. So eliminating that one multiplication is not nearly as important as making sure you have that cache hit. And we're like, this is a serious difference in speed, right? So let's have a look at an actual example. Here's an example. You've got this array up here. This array is 1024 times 1024, which would be a million, right? So this is about 64 million bytes of or 64 million integers times 4 bytes. So we've got a lot of, you know, enough here so that it might take a little bit of time to perform this calculation. 64 million integers. The first loop goes over every integer and multiplies it by 3. So what this loop does is it goes through all 64 million of these integers, takes each of them, and multiplies it by 3. So this does 64 million operations. The second one, every 16th integer is multiplied by 3, right? So this is not a trick question. Which one of these does more work? First one. Quite obviously, it does more CPU work. Which one of these, theoretically, as you've been taught, runs faster? 2. It does less work. But they take the exact same amount of time. Even though loop 2 does 6% of the work, it takes the exact same amount of time on the wall, on the clock, to perform this operation. Why? Well, 64 bytes are being fetched with every lookup. So we've got exactly 16 integers that are being fetched every single time we look it up. So what's happening up here? Our first integer is being fetched from RAM. It's not in cache yet because obviously we haven't looked it up. So we look up array 0. We actually get the next 16 values. So that one lookup, if we look at our previous slide, if we had a cache miss, let's take these numbers as gospel here, to look up that value took 200 cycles. Then those 16 multiplications took what? What's 16 times 3? Less than 50 cycles. So the operation that took the vast majority of that time was the looking up of the data. Right? So by the time we're looking up the next thing, we're already done the multiplications. Down here, what's happening? We're looking up each 16th thing. And if we, on this architecture, happen to have 64 bytes that's fetched with each L1 cache lookup, then every one of these is also a cache miss. Right? So up here, it was 1 cache miss, then 15 cache hits. So one big expensive operation and a bunch of instantaneous things. Then down here, even though we're only doing each 16th thing, each of them is the expensive thing. So what happens is, if you look at a graph of this k value, so if you write the same loop with different values of k, well, 1, 2, 4, 8, 16, if all of those, even though they're doing variable amounts of CPU work, it's the same number of cache misses that are happening, and so it takes the exact same amount of time, right? It's only once you start doing such a few amount of lookups that it's different. Like here, 16 is a good number because we fetch exactly 16 integers in each cache lookup. Down here, once we get to 32, we're doing half those amounts of cache misses, right? And then down here, we've got a quarter that amount of cache misses, et cetera. And this peters out towards the bottom. But you can see that like that line, if I had to give you this on an exam before this lecture, you would have basically drawn a line like that, right? Theoretically, this line should look like this. Okay, this is a log scale. So this line should actually be like this. That's what you should have drawn, right? But it's not. That's not the case. It's crazy, right? That it takes you on, like, I could have just not had this lecture and you would never have known this maybe unless you went out and looked at it yourself. Okay. So example number 1 explained, which I just did. Memory access dominates the running time of that program. Each cache will grab 64 bytes, which is 16 integers. Loop 1 has 1 normal lookup and 15 cache lookups. Loop 2 has 1 normal lookup, but 1/16 of them. So similar memory access time. And the multiplications are pipelined, right? They're probably being done in parallel. They're completely negligible, right? Your compiler is probably smart enough to even like SIMD some of these things. What does that mean? It means that all this is doing is taking each of these values and multiplying them all by 3. So one calculation is not dependent on the previous calculation. Some compilers are smart enough to know that and say, oh, I could probably do 8 of those at a time with my SIMD multiply 8 things thing. But maybe it's not doing that. Maybe it is doing that. That's up to the compiler. So yeah, the multiplications there are negligible. Here, that graph that I showed is from the gallery of preprocessor cache effects. The gallery. It's like it's in the Louvre, right? I like that. I like the idea of going into a museum and seeing cache effects. And then there's this one down here called Data-Oriented Design by Mike Acton. He's a very established video game programmer. I highly recommend watching this video at some point if you care about performance. All right. Someone in the crowd in the Q&A in that video, so Mike Acton is like, no, optimize your code, optimize the hell out of it. And someone raises their hand and be like, well, you know, my code has to run on like 50 different systems. It's fine if you're running on the PlayStation, you can optimize for that, but like that's so much work to optimize for like every possible set of hardware, etc. And then Mike just says, well, you're the reason why Microsoft Word takes 15 seconds to open, right? So it's kind of funny. But the other guy was right. You can't spend all your time optimizing. You got to stop when it's good enough. So, cache-friendly data structures. In order to avoid cache misses, we want to store data contiguously in memory, right? We have to have those things right next to each other in the array so that the cache can actually get more of them. Arrays and vectors do this, but certain lists, sets, maps, dictionaries do not do this, right? So if you store something in a set versus a vector, and you're like, why is my program like 10% slower? Might be the reason, because it's not cached. Linked lists often use pointers, and those pointers, like for example, you might have a node where the node consists, you've all done a linked list, but a linked list node has like a pointer to the next node and some data, right? And those nodes may be dynamically allocated. And so every time you add something to the linked list, it's a new dynamic memory allocation. So you want to use vectors or arrays where possible, but statically sized arrays are great. They're never going to be, so again, a trade-off between vector and array. arrays, you know you're putting data in, the array is never growing or shrinking, so it's never using any more dynamic memory allocations. But you may want to put more things in the array than the size of the array. Similarly, vectors, here's a note on vectors, it is a dynamically sized array. So the trade-off is that yes, it may need to change in size, and that has a cost, but at least it's allowed to change in size, right? Whereas an array is not. So when a vector is filled, it creates a new, larger array and copies everything over. So what will happen is, I have my array, let's say I can currently store 16 things, I'm adding my 17th thing, so it checks and says, okay, let's make an array that's maybe twice as large, put all the stuff in there, and then free up the previous array that I had, and then set this one, right? So some process of resizing goes on, and it's not magic, it has to create a new array. So this is not only a new dynamic memory allocation, but it has to copy all the data, right? So that's very expensive. So one thing that you can do when you allocate a vector, at least in C++, is you can reserve an amount of space equal to some maximum size. So for example, you can call vec.reserve. So if I say standard vector entity v, then I can say v.reserve 10,000. And what I've done is I've resized the internal array to 10,000. So the size of the vector is still 0. There is still nothing in it. It's still empty, but it has room for 10,000 things. So it uses a single malloc, right? Probably uses realloc. And then all the RAM is used immediately. So the downside is that this vector is now quite large with nothing in it. So we're using that memory before we're using the memory. But this means that inserts into the vector will not reallocate the vector until we get to that max elements. So for example, if I know, hey, I'm really never going to have more than 10,000 entities on the screen, then the first thing you do is reserve 10,000 in that vector, and you're pretty much good to go, right? Now, the good thing is, even if the 10,001th thing, 10,001th or 10,001st? 10,001th? We're going with that. Okay. So the 10,001th thing is inserted. The vector can still resize. You've just set it up with a good initial size because, you know, when it's smaller, there are far more of these reallocations going on. So you're setting up with some big size. But you have to do that manually, right? You have to say, reserve me this space. Okay. There's also, hey, how are we actually storing the stuff in the vector? So let's say we have some data. That data could be our entity, for example. So right now, our entity stores a tuple of all the components. If you've actually looked at that, it's a tuple. And a tuple is contiguously stored, right? So all of our components are stored contiguously inside of our entity class. So storing raw data in vectors makes it contiguous. Raw data is larger, and it's more expensive to copy. So this is an issue. It's, again, always trade-offs. But there's two ways to store data in a vector, essentially. One is to store the raw data itself, right? Do I store my entity in the vector? All the data for the entity. Or do I store pointers in the vector? Pointers to data. If I do the first, then it's contiguous. That's better for cache. If I do the second, it usually means that it's non-contiguous, right? Because each of those pointers, now that pointer there doesn't need to be a raw pointer. It could be a shared pointer, like we're currently using, right? Our entity manager class has a vector of shared pointers of entities. And so those shared pointers are all, like those entities are wherever in RAM. They're probably not contiguous at all. And so pointers, let's say the vector does have to resize at some point, right? So if the vector does have to resize, if it's up here, this one has to copy way more data than this one, because down here we're just copying integers, which are the pointers to the data, right? So up here, it's contiguous, but slow resizes. Down here, it's non-contiguous, maybe, but not cache-friendly, right? Because every time we look up a new entity, it's somewhere else completely in heap memory. And if it's a standard shared pointer, just assume that everything is a cache miss, which is unfortunate. And so right now, Entity Manager does have a vector of pointers. And so every single time we go get an entity, it's a cache miss. Every single time. So if you go get an entity, and then you do 50 multiplications, the getting of the pointer to the entity was way slower than the 50 multiplications. So yeah, our engine is good enough right now for our class, but let's see how we could change that if we're actually making a AAA assignment 4, right? Okay. So this is that first example where you've got your cache line. Let's say this is 64 bytes, and then your data, your entity, is 32 bytes, right? So every cache could fetch 2 entities. That's great. That's cutting down on the lookups. So contiguous data allows us to fetch multiple data at once and then have more cache hits. However, with a cache, with pointers here, what you are caching is not the data being pointed to, but the pointers themselves. So that's kind of useless, right? Because then you have to go look up the data from the pointer. So the fact that you're caching the pointers doesn't really matter. Doesn't give you any benefits. So the pointers are cached, not the data that they point to. So each dereference of those pointers will probably be a cache miss, unless the data it points to is contiguous. And so if you've set up something crazy efficient on the back end, then okay, maybe this is good, but probably not. So ECS and caching. Entities are containers for components right now, right? And the currently in our engine, entities contain all the component data in these tuples. And so tuples are great because they're contiguous. So if we ever do get an entity, if all the entity components fit in the cache line, that's great because the entire entity is now cached. So once we do, so we'll look up an entity, right? That's a cache miss. So it takes 200 cycles or whatever. But now, because we've stored the data for the entity contiguously, when we look up the first component, the second component, the third component, the fourth component, all of those will likely be cache hits, which is great, right? We want that to happen. That will be really good. Or is it? Is this what we really want? Okay, Dave, you said the whole entity is in the cache. That's great. But, okay, this is where it gets a little bit complicated. So now we've got our cache. Maybe we get a couple of entities in the cache. So we have cache miss, cache hit, cache miss, cache hit. Even if we had a really small entity where it was like cache miss, hit, 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 right? That would be great. So if entities are stored in a vector, they are contiguous. So the cache could load multiple entities. But we currently store a shared pointer of entity, so this is not happening. But let's pretend that this is the way we're doing it. Okay, we're storing raw entities. So the cache can actually get like 2 full entities. So any component of those 2 full entities, like let's say it has 8 different components. Each time we look up a component, oh, it's in the cache, that's great. Look up the next entity, oh my god, that's in the cache, that's great. All its components are in the cache, super fast. All right. But here's the caveat. Entities are stored contiguously, but components of the same type are not. Why does this matter? So here's what our cache looks like, right? We've got entity 1, component 1, entity 1, component 2, entity 1, component 3, entity 1, component 4. So we've got a full entity in the cache, maybe even 2 full entities in the cache if our entities are super small. Sounds great, but is it what we want? Storing entities contiguously makes intuitive sense, since the cache can then fetch multiple of them. But the important thing is that caching is about access patterns. It's about how we access the data. So, how we want to access the data inside entities determines how we should store the data. Right? And in our minds, what we're doing is we're iterating over a bunch of entities. Right? So of course we want entities, entire entities in the cache, because I'm iterating over entities. But let's look at what we're actually doing in our game engine. We think we're iterating over entities, and we want them cached, but that may not be the case. Well, here's what I showed you before. For each entity, get its transform, add its velocity to the position. That's one system. Another system, get the sprite and draw it. Another one, get the bounding box, get the transform, do some calculation. Look at this. The color coding are the components that we're using. In the first one, we're only using the transform. Why would we want the entire entity to be cached? We're using the transform of one entity, the transform of the next entity, the transform of the next entity, the transform of the next entity. And the entity, okay, so what? We've got a whole entity in cache. Every transform lookup is a cache miss. Right? Down here, same thing with the sprite. Now, okay, this is a contrived example because the sprite probably contains texture data, which is very large anyway. But the point here being that ECS systems usually only access one or two different types of components to do their thing. Right? The gravity system is probably only going to take the gravity component and the transform component. Right? So, given this access patterns, we would want the similar components to be cached rather than entire entities, because we're not doing operations on all the components of entities. If we were, that's what we would want, but we're probably not. So components are small. We can fit many, many more components in the cache line than we can full entities. So this is what we just saw, where the cache contains all the components of a single entity, but probably this is what we would want to have, right? Where we have one cache lookup. So in the cache are a bunch of different components. So we would want to have in the cache component 1 of entity 1, component 1 of entity 2, component 1 of entity 3. So this would be the transform of the first one, the transform of the second one, the transform of the third one, right? So this is what we would want. ECS systems operate on similar components. Contiguous components means more cache hits. But how can we achieve that? Right? Because in order for the components to be contiguous, but they're inside entities. Right? Entities store components. So this entity stores all these things contiguously. How could we can't possibly have them all line up. Right? They're in different components. So I'm going to show you how we could accomplish this with something called a memory pool. And so bear with me for a couple slides. I'll get back to that contiguous part. So a memory pool is a pre-allocated chunk of memory that will be used for the storage of a given data type. And usually a very specific data type. It's not generalized. It's for a specific data type. So for example, for our entities. By pre-allocating the space, we don't need to use dynamic memory allocation, but the trade-off, because there's always a trade-off, is that you need to know the maximum size beforehand, right? Or deal with the very slow copying of all your entities if you run out of memory. Okay, so let's say I'm never going to have more than 100,000 entities, so my memory pool is size 100,000. The downside of that is that now you have 100,000 entities worth of memory allocated right up front before your game even starts. So it uses more memory, but the speed is typically what we care about. So here's the memory pool. I've drawn a table here. Hopefully you can see that well enough. And the way we are organizing that is that up here, this is what we're doing. This dark gray thing up top, this is a vector of entities. Okay? And then down here in the columns, I'm just drawing all the different components. So what we have up here in our current example is that, let's say we're storing entities contiguously in a vector. So this entity is stored contiguously, this entity stored contiguously, this one, this one. So what we have, as we add more entities to this vector, we have, okay, if we were going to access entity 0, maybe all of these things are in the cache, right? Because all of these different components are part of this entity. So this is not a 2D table that we're storing in memory. I'm just showing that entities are contiguous, but each entity has a bunch of components, right? So let's say we've added a bunch of entities. This is what we have, right? We can keep adding things, and now we can say something like, oh, just get the next available memory address. It's much easier and much faster than looking things up with malloc and then getting a new entity position, etc. So the memory pool can eliminate all dynamic runtime memory allocations by being big enough to fit the entities that we want. And so we're going to trade this upfront memory for runtime speed. When a new entity is created, all we need to do is find an empty spot for it in the table. So we can just go, oh, empty spot, right? Much faster than this huge operating system lookup. It's much faster than malloc in practice. The simplest possible thing you could do is just scan left to right for an available spot for an entity. When an entity dies, just mark its space as available, right? And then we also can save time by not deleting dead entities. So we don't have to call free either. And I'll show you an illustrated example of this. But look at this. Instead of storing vectors of entities, let's instead have a vector of each component type. So instead of having a vector of entities, you have multiple vectors for each component. So instead of the columns being continuous, or contiguous, we're going to change it so that the rows are contiguous. So what we had before was that we had one vector going left to right of all of these entities. Now what we have is treat C1 as a vector of all the component 1s, C2 as a vector of all the component 2s, C3 as a vector of all the component 3s, etc. And then what the entities now represent is just the index of each of those vectors where my components are stored, right? So if we have entity 3 up here, then in order to get component 2 of entity 3, well, if E3, let's just say it has an integer of 3, for example, we would look up the vector of C2 indexed by 3, and that is the component. So rather than have the components stored inside the entity class, all the entity is now is an integer. And then the integer tells you where to look up the data in the memory pool. Okay, so the entity class will no longer store, yeah, question?
Would you have like an integer for each component, or is it one integer for all of them?
So you don't have an integer for each component. The components, that is a vector, right? So C1 here is a vector of all the component 1 types. So this might be a vector of all the transforms. This might be a vector of all the gravities. This might be a vector of all the animation, right? And now what the question you're asking is, how do we know which vector is which? And
because you said that you look from left to right in each vector to find an empty space. Wouldn't it mean that, for example, C1 has like an index?
I'll have an example of that. So just give me a couple slides. So the entity class no longer stores its components as member data, right? The entity now, literally, if like I've implemented this in the game engine, not for your assignments, because you don't have to do that, but the entity just contains an integer. That's the only member variable of an entity anymore, is an integer. And so because of that, you can pass integers around all over the place. They're trivially copyable. It's just an integer, right? And entity functions, instead of getting the data from within themselves, they're now looking up the data in a memory pool, right? And they just look up, hey, look, you want to get the transform component of me? Okay, go to the transform vector and look up the data in this index that I have stored. How the hell do we implement that? Luckily, in C++, it's pretty easy. Because I can have a tuple. Instead of a tuple of components, which we now have inside the entity, we can have a tuple of vectors of components. And this is essentially our memory pool. And then to get an entity's component of type T, well, we have this entity component vector tuple. That's what I've defined this as, right? And so if I want to get the component of type T from a specific entity ID, we say standard get standard vector T, which is a super fast lookup because C++ does this very efficiently. So that will say, oh, I want the transform component. So it will get the vector of transforms from this tuple in constant time, essentially. And then of data, so that's where the data is. And then that's a vector, and we look that vector up by the entity ID. So that's how we get it. And then let's see how our system changes if we want to implement something like this. We would have an entity memory pool class that we're going to, we're nice object-oriented people. So we're going to have, keep track of the number of live entities that we have. We have the actual vector storage tuple. So that's for the components. But our entities have other things that are not just components. They have a tag. They have whether or not they're alive, right? So we have separate vectors for each of those. And then we have a constructor. And down here, we are going to make sure that there's only one memory pool ever allocated. And we're going to do that with a singleton pattern. We talked about the singleton pattern earlier. And so we can get access to our memory pool with this instance. Yeah, I talked about that. So we allocate our memory pool once here. So we have a static entity memory pool. So there's only one of them. It has some number of max entities that it can store. And then whenever we get this, we return it. So our entity memory pool, the getComponent function of the memory pool would take in an entity ID because we want to get the tuple for, we want to get the component of this particular entity ID. So we would say return standard get standard vector t of our data indexed by the entity ID. Okay? And now when we do this, when we say get the transform of entity 1, what we've also gotten in the cache are the next few transforms. Right? Because they're all contiguous in that vector of transforms. Down here, if we wanted to get the tag, then we would just look up the tag. Right? So we have one tuple for all the components, and then we have all the different tags stored separately. The tags and the bools, etc. And then the entity class would change a little bit. So it would only be storing an ID. That's the only thing that the entity stores is an ID. And all we have to do is change our getComponent, or addComponent, getComponent functions so that now, instead of taking from the tuple that used to be here, we say entity memory pool instance.getComponent t of this ID. And so that's how it would change. And the really cool thing about this is that the only thing we had to do was write a memory pool and change the entity. None of our game code changes, right? So one day, you're the gameplay programmer, you're doing the physics, right? And you've been benchmarking, oh, my physics takes 20 milliseconds, takes 30 milliseconds. And then one day, you pull the changes from Git, and now your physics is taking 5 milliseconds. And you're like, what the hell happened? My code didn't change, but someone wrote a memory pool, right? So you literally don't upset anybody. You've optimized in one place, and now it just works. And I'm still calling addComponent, getComponent, setComponent, removeComponent, but in the back end, it works differently. So in the entity manager now, the entity manager would have to make a call to the memory pool to add the new entity, right? So no longer is it saying new standard shared pointer and asking malloc or the operating system where to store that entity. You're asking the memory pool where to store that entity, okay? And inside the memory pool, the thing that we now have to do, the most complicated thing of the whole process really, is the add entity. So if we want to add an entity, we essentially have to have some function which says, hey, get me the next free index in the memory pool that I can actually store something. Okay? So you would then, once you get that new index, you basically have to zero out all the data of those components, which is still less expensive, far less expensive than creating a new component, a new entity on the heap. And then you set its tag, you set that it's active, and you return a new entity. And again, an entity is just an index now. So it's just, you just say entity index. So when we create the memory pool, we have many copies of blank default constructed component of each data type. So each component has a Boolean associated with whether a given entity actually contains that component. So the thing we were doing before is that we were checking to see, remember when we had pointers to all our different component types, right? So if we didn't have a component, it hasn't been set yet, and so we know that it hasn't been set yet. So we call it hasComponent thing. But now, all of our components are already default constructed. And so we have to have a way of saying whether or not that component is actually being used. Because it's already constructed, it's there. So what we have is this active Boolean saying whether or not okay, this component exists in the table. It always has to exist. It's persistently existing in the table, but whether or not it actually is set in the entity, right? And I'll show an example of this. Okay, here's the example. So we've got an entity memory pool. We have default constructed everything, right? So the memory pool has been set up once. There was a big call to malloc. We've got 100,000 blank entities that we can now work with. So this is a vector of all the transforms. This is a vector of all the gravities. This is a vector of all the lifespans, whatever. This is a vector of all the tags. This is a vector of all the, whether or not this entity is active, right? Because if we're iterating through this thing, we've got to know, okay, is this actually an entity that's active in our game? So when we want to put a new entity in the memory pool, we need to find a location to put it. The simplest way, just scan from beginning to end and find the first location excuse me, of a non-active entity and use that slot. So let's have a look. So F means this entity is not active. So by default, when we start, everything is not active. Let's put something in there. So what happens? We say entity manager.add entity P. Entity manager calls the entity memory pool and says add a new entity with tag P. So up here, what this means is that C1 has some data associated with it. Now, it's probably not just going to be a single integer, but this is just for illustrative purposes. This F means false. This component has not yet been set, right? The data is there. The data is alive, but the component has not been added to this entity yet. That's why that's false. Down here, active means true, right? So this is an active entity that is alive in our game somewhere, and it has a tag of P. Now, let's add a component. So to add a component, C1, all we have to do is set that to true. So that's what the entity manager does, or that's what the memory pool does. By adding a component, we say, okay, that's true now. That's it. I've set one Boolean variable. There's no dynamic memory allocation call. I'm not creating a new component. I'm not doing any of that. It's just called. Then, oh, I don't know why the font just changed. That's weird. Entity, we call the entity p.getComponent c1.value equals 7, and we just change the value here. That's all that's happened for that call. All right, let's add a new entity to the entity manager. Well, we scan from left to right. The first one was true. We can't use that spot. The next one is false, so we can use this spot. So we've added Q, this entity. It has no components active. This is true. It says add component C2. So what does this do? It just sets this to true. Then getComponent.value is 3. Okay. Now I say remove component C2. Literally, all this does is set this to false. I don't even need to touch the data that's there. I can just leave it. So to remove a component, it's literally just setting a Boolean. Because later, if I call, let's say I call p.destroy, okay. If I say has component, what has component does is it looks up the component and checks this variable. So this would say, if I say this entity dot has component C2, it would look up this F and say, no, I don't have it. I don't have this component. Even though there's data there, I've removed the component. Okay. All right. Now let's say we want to remove an entity. So I call p.destroy, which sets this to F. Now in the entity manager, we still need to keep a vector of the entities that are alive, but now that's a vector of entities which are just integers. So that's super efficient, right? So I still, yes, somewhere I still do have a vector that I need to go through and remove the dead entities from, but that is a vector of integers now that point into this thing. So it's like super efficient to have. Now I'm going to say entity R equals entity manager.add entity R. And look, if we scan from left to right, if we want to add a new thing here, well, I've got some data here, this 7, this T. In order to destroy an entity, I didn't have to call free on the heap. All I had to do was set this to F. So destroying an entity, all it does is set one variable. Super efficient. No dynamic memory at all. However, now this is free, so if I scan left to right for a new one, I'm going to put it here. So what I do is, whenever I add a new entity, I zero out all that data back to the default. That's when I take all the stuff and zero it out. Okay? So this adds a new entity manager, add component C3. I would say, okay, now I have this T there. And now when I call my stuff in my systems, all of this is all contiguous, right? So if we go back to that example of multiplying all the values in the array by 3, that's essentially what we're doing here. We have a bunch of transforms. Now, if we make our transform too big, right? So for example, our transform now has like position, previous position, velocity, acceleration. It has like a bunch of different stuff in it. So if you make the component itself too big, then you have far fewer of them in the cache. So what we may want to do, if we were being super optimized, is maybe have like a position component that only stores the position, and then a velocity component which only stores the velocity, right? In order to make sure that we get more stuff in the cache, but it's fine. You know, it's easier for your game engine, and your game engine already, even with the shared pointers, can do tens of thousands of entities a second, no problem. This is if you want millions, right? So this is what we have. Now we have all the sprites contiguous. Well, I should really remove this one because the sprite contains texture animation, which is on the heap. So that's not actually contiguous. I just wanted to show you. Down here, even though we have two different components that are being used, so we have the bounding box and the transform, well, the first thing we call from the bounding box, that's going to cache a few bounding boxes. And then the cache has more room than just one thing in it. And so our transforms are cached and our bounding boxes are cached. So when we get the next entity, we've got the next bounding box and we've got the next transform as well, right? So it's a pretty cool thing. And it really does speed up your program. However, there's one downside that I've run into personally with having a memory pool. That is, recall back to 3200, if you did 3200 for a second, where we have a game state, right? So you have a game state for something like A star or alpha beta search, where I would want to be able to copy a whole game state and do a search. Copy a game state, copy a game state, copy a game state, right? And then like, forget about this game state. That's really easy to do if your scene has an entity manager which stores all of the entities inside the entity manager. I just create a new entity manager, create a copy of that entity manager. Now I've got a copy of all the data. But if you've got a Singleton memory pool that stores everything, copying your entity manager now, all it does is copy the vector of integers, right? And so now you've got a second state, but those integers, your entity integers, for both states are the same, and so modifying one is going to modify the other because it all points to a single value. So if